I want to welcome you to another statistical class. Today, we're actually going to start a new topic and, of course, a new chapter. And that's going to be chapter 4 from the recommended textbook. We call this chapter mathematical expectation. Of course, there's a reason in statistics why we do what we do. What is the essence of mathematical expectation? Of course, what you want to learn today, you're actually going to see the benefits of mathematical expectation, because with mathematical expectation, the stakeholders in whatever field, they can actually measure what I call risk analysis, and they can also going to make them to plan, because mathematical expectation is actually talking about on the long run. Even though we know we live in a stochastic world where things varies, right? Then on the long run, okay, mathematical expectation will provide a measure of what we can expect to happen. But before I go into the topic, four of us want to say Happy Valentine's Day to every one of us, even though I know every day should be Valentine. Every day should be a day that we love. But there's something I'm also want you to know. We've been talking about random variable, but I want you to notice love, unlike random variable, okay, unlike random variable, defies quantification. You know, with a random variable, right, we're able to quantify, right? We're able to understand environment probabilistically. Okay, so love, unlike random variable, defies quantification. So it is a complex emotion. Okay, it is a complex emotion that transcend statistical analysis. Statistical, statistical analysis or mathematical uh analysis. Okay, so why statistics provide, okay, an insight, provide an insight into um physical, or into the behavior in the physical world, into the behavior, okay, in the physical world, in the physical world. So the depth and intricacy of love remains remains in its remain let me see, remain beyond its reach. Okay, so what is the essence of all this? I'm just trying to say there's no way love can be quantified. We should show love to one another. So, and unlike in statistics where you can actually provide a definite answer, a definite, that. So we should continue to love. There's a beauty in diversity. Okay. Now I used to tell people around me that, if I claim I'm greater than you and somebody else is going to be greater than somebody that is greater than me, the greatest person on earth is less than supernatural being that we may call God in a way. Okay, so maybe there's a reason why there's variation, but variation did not start now. I believe variation starts from the beginning. And reason for variation, reason why we don't look the same, is just for us to appreciate our beauty. Imagine this place, if you are wearing the same shoes, the same dress, it's not, the world is not going to be eventful. It's going to be so dull. Okay, now coming back to the mean of random variable, let me tell you this. I can't talk about mean of a random variable without first understanding what is the nature of the random variable. Is it discrete or continuous? Because when I know the nature of the random variable, I will be able to know the appropriate probability distribution. Because if I want to compute the mean, if I want to compute the mathematical expectation, I need to be able to know the nature of the random variable. I also need to know the probability distribution of the random variable. So you are welcome to the mean of a random variable. But let me tell you this. What do we mean by the mean? That's an average. That actually means what we expect. Even though we know things varies, right? When we produce, the amount we produce today is going to be different from the one we're going to produce tomorrow. There's a natural variation that is inherent on anything we do. But on the long run, what do we expect? That is what we call the average. That's what we call our expectation, okay, of an outcome, okay, even though we know the outcome varies. Okay, that's what we call mathematical expectation. So in a stochastic world, we always going to talk about mean, because things don't happen. We normally have a different value it shows in any given situation. So, and as human being, we actually want to know on average. But let me tell you this: average is not the same as reality. But average, the mathematical expectation, we only give you some kind of picture of reality. Does that make sense? And that's why I want to go into that now. Now, we want to start again. Now that you understand our intention here, we don't do what we do. There's a reason, okay, why we do what we do. I told you the other time, if I want to figure out the mean of S, we can call it the mean of S, we can call it expected value of S, we can call it mathematical expectation of S. Now, I want to tell you now, if S is discrete, this is the formula. I told you the other time that if I want to figure out the mean of a random variable, I need to first ask myself, what is the nature of the random variable? Am I talking about discrete or talking about continuous? Now, if I'm talking about discrete random variable now, and I want to figure out the mathematical expectation, is going to be summation S, f of S, where you're actually going to be summing over X. Because X varies, S is actually going to have state space. Now, that is when, if S is discrete. Okay, but what about if S is continuous? Well, how would the formula change? Oh my God. Take a look at that. When S is continuous, it's actually going to be integral over the state space of the random variable, S f of S ds. Okay? You can see the formula now, right? Before you're going to perform an antiderivative here, you need to first multiply the random variable S by the probability density function, the probability name or probability distribution name for continuous random variable is what we call probability density function. So which means if I want to figure out the mean of S, that we also call the mathematical expectation of S, or we also call the expected value of S. Of course, we're actually going to perform an antiderivative between the product of X and the probability density function. Now, this is so I've given you two situations now, two scenarios, okay? And that's why I was telling you the other time, okay? You need to be able to figure out, are you dealing with the discrete or you dealing with the continuous? Now, I want to go into example now, and I'm actually going to start this example from discrete. Okay, I'm going to start this example now, okay, from discrete. Okay, now I need you to pay attention. Okay, now we actually want to have, assuming that one fair coin, one fair coin was tossed twice. Okay, don't forget. How do we normally have? Take a look at this. If I want to find the mean of a random variable X, I need to first understand this. There's going to be an experiment. Experiment will generate an outcome, and there's going to be a sample space, right? That contain a possible outcome. And of course, in the sample space, you need to be able to for define your random variable. Okay, now in a coin, in a balanced coin, we got two sides. We got head, we got tail. Before you actually assign numerical values to the element in the sample space, you need to for define what is your variable of interest. Oh, out of the two sides, which one am I looking for? Oh, I'm looking for head. Or somebody could say I'm looking for tail. Now, I need you to take a look at this. This is the sample space when a coin is tossed twice. Does that make sense? Which is a possibility. When a coin is tossed twice, there's possibility we could see head, we could see head, tail, we could see tail, head, we could see tail, tail. Now, we define our random variable to be the numbers of head before we go into the experiment. It's just like a businessman before going into business. What do you think a businessman or woman has in mind? Profit. Even though he has not even invested, but what he has in mind, what he or she has in mind is to make profit. But don't forget, within the sample space, there are possibility it could make profit or loss. Now, take a look at that. Now, our random variable X here represent the numbers of heads. Okay? You are going to be the one that depends on what you're looking for. Now, if it is the numbers of head, then we're actually going to have a state space here, which is going to be 0, 1, 2. That's going to be the state space of X. 0, maybe I don't see a head. That is state tail. 1, I see one head, either the second or the third. And of course, I see 2 X, which is that one. Now, I know my state space will be 0, 1, 2. I've defined my random variable. This is a discrete random variable. Then if I have a value, if I have a possible value for my random variable, which is in this case, X equal to 0, X equal to 1, X equal to 2, then we need to be able to find what is the probability associated with the outcome. Because if I want to find the average, I need the knowledge of both the state space and the probability. Now that's what I'm doing this. Take a look at that. I want to find the probability of S equal to 0. S equal to 0 means when I see tail, and of course, when you take a look at the sample space, we got 4 possibility. The probability is going to be 1/4 because element in the sample space has equal chance of occurring. Now, probability of S equal to 0 now is the probability of theta. It's going to be 1/4. I also need to get the probability of S equal to 1. Then I need to get the probability of S equal to 2. Now, what have I done here for the possible value, okay, of the random variable 0, 1, 2? I've been able to obtain their corresponding probability. The probability here is just trying to talk about frequency of occurrence of this random variable. Do you now know I'm set? Now that I have the possible values of a random variable with their corresponding probability, I'm set. I can now compute mathematical expectation around this. The mathematical expectation around this, I want to know on average, how many heads am I going to see on average? That is what we mean by expectation of heads in this case. Now, if I want to do that, I should be ready to use the formula that I showed you the other time. You know, the formula is this: expectation of x equal summation x f of x, okay, and x here is going to start from 0 to 2. Oh my god, that is what I'm actually doing here. I use when x equal to 0, multiply by its corresponding probability, plus when x equal to 1, multiply by its corresponding probability, when x equal to 2, multiply by its corresponding probability, and actually give 1. So which means expectation of s equal to 1. What does that mean? Okay, it actually means on average, when I toss a coin twice, then on average the numbers of head I'm actually going to see is 1. That's what it means. Okay, and that is why I actually have this interpretation here. I said this result means that a person who tosses 2 coins over and over again, you know what I say, over and over again, okay, that means the person is having a repeated experiment. Okay, on average we get 1 head per toes. That is what we mean. Does that make sense to everyone? Get 1 head per toes on average. That's what we mean. Okay, now if that is taken now, I actually want to move. Okay, actually want to move. I need you to take a look at the example 4.1. You know, in the last example, we perform an experiment with a coin, and of course, our mind can never be empty. We got certain variable in mind. You know, we want head to occur. Okay, now, and we computed the probability, and of course, we're able to find the mathematical expectation. But I needed to take a look at this example now. A lot containing 7 components is sampled by a quality inspector. The lot contains 4 good components and 3 defective components. Now, I need to take a look at this. 4 good and 3 defective. That is the variation we're talking about. Okay, when we produce, even though we're using the same equipment, the same number of people, what we produce, they're not going to look the same. Some will be defective, some actually going to be fine. That's a variation. And you know what? Whenever there's a variation, the knowledge of probability can be applied. And when the knowledge of probability is applied, we can figure out the mathematical expectation. Now, a sample of 3 is taken by the inspector. Let me tell you this. The first information that you see is, okay, when they look at the history of production in the company, okay, for every 4 good components, they normally have 3 defective components. Now, every company has a quality control unit, particularly those that are into production, because before they actually ship whatever they produce to the public, they got to make sure that there's a conformance. So the quality control section in a company will ensure compliance to conformance. Okay, now it's so if they want to, but let me tell you this: if a quality control officer want to investigate, they don't investigate all items to produce. We don't have resources for that. They're only going to take a sample. Okay, now here now, you take a sample of 3. If a sample of 3 is taken by the inspector, now find the expected value of the numbers of good components in the sample. Here, what are we focusing on? It's trying to tell us the random variable in this question is focusing on the numbers of good components. In another question, I could be focusing on the numbers of defective. Does that make sense? Now, we're not going to X is now, that was why I said let X represent the numbers of defective. The numbers of good component, because the question actually centered on good components. Now, we're now going to take a look at this guy. I need to take a look at the denominator. In the complaint, we're actually going to assume the total numbers of production is 7. Then how many do we want to choose? Just 3 out of 7. This guy means 7 choose 3. Like we're choosing 3 out of 7. The possible numbers of way that can be done is what you see. Now take a look at the numerator. The numerator is partitioned into 2 categories. The first category, good ones. The second category, defective. Okay. How many good ones are we told? 4. How many bad ones? 3. And you can see 4 plus 3 is 7 in the denominator. Now, X, we said X represent the good ones. That is going to be the good one in the sample. The good one will come from the population of the good. X, because it's the numbers of good in the sample, it's actually going to come from 4. Which is 4 is the population of the good ones. Now, 3 minus X. Why 3 minus X? Because which means I'm partitioning my sample of 3 into 2, into 1, into X, and 3 minus X. If X is the numbers of good in the sample, then the numbers of bad in the sample will be 3 minus X. Because I choose a sample of 3. Does that make sense? Now, this now become the probability distribution for a random variable X. And what does the random variable X represent here? The numbers of good products. Now, what is the state space? If I choose a sample of 3, like in Spero here, choosing a sample of 3, what are the possibility? S equal to 0 means no good ones. S equal to 1 means only 1 good. S equal to 2 means only 2 good. And S equal to 3 means all of them are going to be good, which are possibility, which is what we call the state space. Does that make sense? Okay, now, do you know that using this guy now, I can use this function to figure out when S equal to 0, what is the probability of X? When S equal to 1, what is the probability of X? And so on like that. That's what I'm doing here. Okay, when you take a look at this guy now, this guy, okay, and this guy, we're plugging in the values into that. They use a calculator to compute that. And for every value of a random variable, now we are able to compute the probability associated with that. Now, this guy is trying to tell me, if you really want to know, if you really want to interpret this guy, you can multiply each of these by 100. And that will tell you the numbers of times out of 100 that they're actually going to record 0 good out of 3 that he mentioned. 1 good, 2 good, and 3 good. Does that make sense? That's exactly what we mean. And the moment we have that guy, we can now figure out the mathematical expectation, which is the average of the numbers of good. So the average of the numbers of good is just for you to multiply the values of the random variable by its corresponding probability. Is there any question here? What are we trying to say at the end of the day? We got 1.7, right? What are we trying to say if a sample of size 3 is selected at random over and over again, not just once, over and over again, from a lot of 4 good components and 3 defective components, this is based on 4 good components and 3 defective components initially. It will contain on average 1.7 good components. Is there any question here? Go ahead. That's a very good question. You may not necessarily need to know in this topic, but in chapter 5, we call that hypergeometric distribution. So we're still going to talk about probability distribution. That's a good question. But here, what I'm just going to give, I'm actually going to provide you with a function. Okay? That's a good question. Thank you for asking that question. Now we want to move right now. We're moving now. We're moving like a moving train now. Okay, go ahead. Oh, okay. Uh, I want to believe you're talking about this guy, how I put it, the values of X in, getting the probability, right? Now the first one, let's say I want to get for the probability for X equal to 0. It's actually going to be 4 combination 0, 3. 3 minus 0 is going to be 3 combination 3 divided by 7 combination 3. Now your calculator, okay, you just need a choose. There's something like a combination. Okay, 4 choose 0. I think should be 1. Anything choose 0, anything combination 0 is going to be 1. Then when you have the same number, how many times am I going to choose 3 out of 3? That's going to be 1. Then I'm going to do 7 combination 3. So 1 times 1. So 7 combination 3 will give you 35. Do you now understand how we, okay, that's how we do that. Okay, now we want to go into another example. It says specific for a medical device, company has to appointments on a given day. Please, we need you to pay attention to all of this. It believes that it has a 70% chance to make the deal, okay, from which it can earn $1,000 commission if successful. On the other hand, it thinks he only has a 40% chance to make the deal at the second appointment, from which, if successful, it can make $1,500. What is expected commission based on its own probability belief? Let me tell you this: whenever probability belief, okay, take a center stage, okay, we always want to get an average. Does that make sense? Okay, now we need to first figure out what are the possibilities. Don't forget, okay, we actually have 2 appointments. Okay, there are 2 appointments. Let's view these 2 appointments, and we actually 2 appointments to me is looking like tossing a coin twice. Tossing, the other time I show you an example, tossing a coin twice, and in tossing of a coin twice, maybe I'm looking for numbers of head. Okay, now I can have in the 2 tosses, I can have no head, I can have 1 head. Okay, I can have 2 head. Now let's take a look at this for the appointment. Now I may not be successful in this appointment and not successful in this appointment, or successful in this one, not successful in this one, not successful in this one, successful in this one, or successful in both. How many possibilities? 4. That was why we got this guy here. Take a look at that. How many possibilities we can have possible commission total? Is $0 when you lose at both ends. In this appointment, not successful. The other appointment, not successful. If it is not successful, there's not going to be any commission. $1,000, that is when the first appointment is successful. Okay, the first appointment is successful and the second is not. $1,500 when the second appointment is successful and the first is not. Oh my God, this is what I want. This is what I want. Where the two appointments are successful, you hand $1,000 in the first appointment, you hand $1,500 in the second appointment, you had it all. Do you now understand how we figure out, the possibility now? Now that we know this now become a random variable now, the random variable now is the amount you hand on commission, which varies. But what do we want to do? We want to figure out on average, what is it going to be? If I want to figure that out on average, then I need to know the probability associated with each. And how am I going to get the probability? How am I going to have access to the probability? Oh my God, this guy says something here, 70% chance of making a deal in the first appointment and 40% chance of making a deal in the second appointment. Now, let's take it now, putting that into consideration now. Please, with the law of complement, I need you to say this. We want to find when s equal to 0. What does that mean? S equal to 0 means not successful at both appointments. What is the probability of being successful on the first? 0.7. Then not successful will be complement of that. That is why it's 1 minus that. We've done complement in this class. 1 minus the other one, not successful, and that probability is 0.18, which means 18% of a time. Okay, it's not successful on the first appointment and not successful on the second appointment using that belief probability. Now, but take a look at this guy. Oh my God, look at that. Successful at the first, successful at the second. You multiply the probability, you're actually going to hand $2,500, and that occur 28% of the time. Now, that is how, take a look at the other one. Any question about all this, how we figure out this probability value? Any question? Okay, now, what we're going to do now? We are set. If we now want to find the expected commission, like on average, let me tell you this. We're not trying to say that is exactly what the person is going to get, but we're putting the stochastic word into play that, okay, on average, and on the long run, is expected to have 1,300. What have we done now? We've made use of the law of expectation involving a discrete random variable where you multiply the value of the random variable by its corresponding probability, you add up, and that end up in $1,300. Any question? But let me tell you this. This value is going to change when the probability of belief change. Does that make sense? Okay. Now, I'm actually done with discrete. Any question on discrete before moving to continuous? Let me tell you, in continuous, the law or the knowledge of calculus will be required. Now, I need you to take a look at this. You're given this. Okay, let S be the random variable that denote the life in hours of a certain electronic device. Let me tell you, every electronic device that we use, we are not going to use them forever. You know that, right? They also have their own life expectancy. It's going to be a time that they're not going to work anymore. Okay, so X now represents the life in hours. Okay, and the life in hour of a particular laptop, even if a company produce the same laptop, 1,000 laptop, they're actually going to have different value of life in hour. Okay, now mathematician, we look at the probability function associated with the random variable here, and we come out with this guy. And they believe that at least the device will spend 100 hours. And of course, the S for S greater than 100, S greater than 100, this function exists. But situation where we are no longer talking within the rhyme of s greater than 100, that function is actually going to be 0. Now that f of x here is a probability density function. Now how do we figure out the mean? Of course, the other time I said we want to figure out the mean of a continuous random variable. We're actually going to have integral f of s dx, where I'm actually going to use, the range. Okay, if you take a look at this, s greater than 100 is going to be 100 to infinity. Okay, I needed to pay attention to this state space. So what am I going to do now? And that is why you can see this guy, right? X multiplied by f of s. Before you perform an antiderivative, you need to first simplify. When I simplify this guy, I'm going to have this guy, right? Then I'm going to do my antiderivative on that. And when I actually perform an antiderivative on that, then I'm actually going to plug in infinity minus when I plug in 100, and that give me 200. Now, therefore, we can expect this type of divide to last on average 200 hours, which is more or less like average life expectancy. Does that make sense? Is there any question here? Super easy, right? Super cool, right? Okay, now, I think I've walked you through how to figure out the mathematical expectation of a random variable A that is continuous and discrete. But this time around, we don't want to focus on just a random variable X. We want to focus on a function of a random variable, g of x. And I'm going to give you this example. Let's say, for instance, I have ax plus b. I got ax plus b. In this case, I'm calling that a g of x. Let's say x represent the number of quantity that we produce. And A is the amount that I spend producing certain number of quantity. A and B are constants. So A, okay, if I produce one of this quantity, I spend A. If I produce more, so then what is B? B is likely going to be maybe a fixed cost. Maybe the cost of getting the building we're using. We pay, we start spending even before we start producing, right? Okay, now if what we produce is subject to variation, maybe what we want to get, the g of s here is actually talking about the total cost. Okay, the total cost. Maybe I want to talk about total cost of production. Of course, the total cost of production is also going to, it's going to comprise, the amount I spend before production and the amount I spend during production. If X is subject to variation, then the cost is also going to subject to variation. So G of S in that situation can also be treated as a random variable. Now, and that is why, which means G of S can be discrete, G of S can be continuous. When G of S, we're not talking about X anymore, but we're talking about a linear combination of a random variable. Okay, a linear combination of a random variable. It could be linear combination, it could be whatever combination of a random variable. When it is discrete, then the G of S is also going to be discrete. And G of S can also be continuous. Here we're focusing on the function of a random variable. A function of a random variable is also a random variable itself. Does that make sense? Okay, it can be discrete, it can be continuous. Now, and this is the example I cited. When I have AS plus B, where A and B, I have AS plus B, just like what I said. Now, AS plus B is a random variable because S is a random variable. Then I may want to find what is the average, the expectation of that. So when I actually use expectation to multiply that, A is a constant, is going to come out. I'm going to have A expected value of S plus B because the expectation of a constant is a constant. Expectation, oh my God, expectation of B equal to B because B is a constant, doesn't vary. Okay. Now, if AS is continuous, I'm actually going to expect a value of that. All of this is a random variable. If it is continuous, then I'm actually going to have it inside here, multiplied by f of s. The f of s is a probability distribution of a random variable. Okay. Now, when you try to simplify here now, where here you're going to be AS before you do antiderivative. AS multiplied by f of s is going to be this guy. And, that multiplied by that, B multiplied by is going to be this guy. And take a look at this. What do we say about that? Integral f of s ds, okay, over the state space, we said that is going to be 1, right? You remember? And if that is 1, then what is this guy? What is that guy? That is the expected value of x. Okay, take a look at this. This guy here. This is the expected value of s for continuous random variable. And therefore, this guy is this guy. This A is here. And this is B. Don't forget I said this guy is going to be 1. Okay, so this is just a proof to show this guy for continuous random variable. Okay, for continuous random variable. Now, I want us to go into an example right now. Okay, we want to go into an example right now. I need you to be focused now. Okay, but this example is actually going to be taken from a discrete random variable. Okay, and we actually want to talk about a function of a random variable. I needed to take a look at this. Suppose that the numbers of cars that pass through a car wash between 4 p.m. and 5 p.m. on any sunny Friday has the following probability distribution. Anytime, any day they give you something like this, you should be expecting a discrete. Because that's listed, right? That's a discrete. Okay. Now, if this guy is discrete, okay, the function of the random variable is also going to be discrete. Does that make sense? Okay. Now, the question now said, let g of s to be 2s minus 1. But I told you, x is a discrete random variable. Then the g of s equal to s minus 1 is also going to be a discrete random variable. Does that make sense now? Okay, now, what is the formula? Okay, if I want to, if I take you back a little bit to 9, do you see this guy? That is the formula to figure out the mean when the random variable under investigation is actually a function of a random variable. It's going to be expected value of gs, which is going to be summation gs f of s. Take a look at that. Now, that is what you're going to apply here. That's what I'm doing here. Give me 1 second. So that is exactly what I'm doing here. Do you see that? Expected value of g of s, and g of s is 2s minus 1. Then it's going to be that f of s. Okay. Now, don't forget, what was the state space? If I want to sum, you've been told here the state space is going to start from 4 to 9. You see the state space from 4 to 9. Can you see that? What are we going to be doing now? What we're going to be doing, now I'm going to come to the 2s minus 1, plug in 4. Okay, what is 2 times 4? 8. 8 minus 1. That's why you have this 7. Okay, now, what is the random variable for s equal to 4? It's 1 over 12. You have already been given. Is there any question about that? Take a look at that. Any question? That's super easy, right? Now, $12.67 now is the expectation of the function of a random variable. The function of a random variable here is 2x minus 1. Does that make sense? Okay, super cool, right? Now I'm going to go to the next example. Okay. Oh my God. This example is actually coming from continuous right now. where g of s, a function of a random variable, is actually continuous. Okay, but you're given this f of s. If the distribution of s is continuous, then the function of that random variable is also going to be treated continuous. Okay, now we take a look at this now. They say find the expected value of g of s, and where g of s equal to 4s plus 3. Okay, if I want to do that, I'm actually going to take you back a little bit into the formula on slide 9. Okay, do you see this guy, right? That's for continuous, right? Okay, that's what you're going to use. Now, in my exam, I expect that before you use a formula, you need to write the formula down, because the formula is also going to be graded. Does that make sense? Okay, now, if you take a look at this guy now, we want to find the expectation of a g of s, and the g of s is 4x plus 3. That is going to be integral using the state space, right? -1 to 2. Okay, then I'm going to write this guy, then multiply by s squared over 3. That's why you have this guy here. You know, when in high school, when you are taking calculus in high school, you normally see a question like this, right? You normally see a question like this, and you're going to be wondering, what is the essence? These were actually formulated from a real life practical situation. Now, what you're going to do now, you want to simplify now, then you actually perform an antiderivative, and at the end of the day, my answer is 8. Take a look at that. Is there any question on that? I will advise that you revisit calculus, okay? Just basic calculus, okay? Not rigorous one, okay? Now, I'm going to go into another example. Oh my God. Take a look at this. At time, we can take a look at it. We can find the expectation of something plus something, or something minus something. We can also do expectation of y divided by x. Y divided by x, if you take a look at that, and if I want to find the expectation of y divided by x now, okay, then I'm actually going to be needing bivariate function, because I got two variables. You remember what we did on that joint. Then you're actually going to be given f of x, y, because for expected value of y divided by x. Now, if you have this guy now, I want to find the expected value. I think this should be a mistake. Correct this guy, not that, because the way it is written is looking like x, y given s is different. This is what I mean. Do you see what I mean? This is y over x, because there's a difference between, even though I know in mathematics, somebody can say 5 divided by 2 as this, 5 over 2. But don't forget, in statistics, we normally use that guy as given. Does that make sense? Now, if I want to find this guy now, you need two integrals. You see two integrals? Then this guy, y over x, is going to be here multiplied by this. You know, if you have y over x multiplied by x into 1 plus 3y squared divided by 4. So s is going to cancel s. You're going to be left with this guy. That was why you have this guy. And don't forget, you're going to do the antiderivative with respect to x using the range, using the state space of x, 0 to 2 first. Then finally, you're now going to do that with respect to y using the state space, and the answer is actually going to be 5 over 8. Take a look at that. Okay, so far so good, right? Now you can read all of that. This is talking about situation whereby I actually want to find the expected value of s, and given that I'm working with it, bivariate, and expected value of y, given that I'm working with that. Okay, that's what that guy is talking about. I think I put more example that you can practice. Okay, you can practice that if you like. How do we figure out the expectation of x in that situation? Okay, so make sure you can try that. Take a look at this guy as well. Okay, maybe in the next class I'm going to walk you through how you can navigate it, but you can try it. I want to find the expectation of z. which means I want to find the expectation of this guy. I want to find the expectation of this guy. Okay? It's going to be integral, that guy. Then this guy, for x, y, that will be two integral. You're going to have the x, the y. Okay? So you can try all of that. I think I put a lot of exercise for you. What is going to be next? Oh my God. What is going to be next is actually going to be the variance of random variable, because whenever we find the average, how do we tell about the reliability of the average? Then we need the variance. Does that make sense? That's what we're going next. We're going to walk you through how do we find the variance for discrete random variable, for continuous random variable, for situation where the function of the random variable is discrete or continuous. We're actually going to focus on that in the next class. Is there any question before I go today? Any question? Is there any question? Oh, be sure you all stay safe and enjoy your day. Bye for now, everyone.